Yes, today in this lecture, we will basically try to discuss organic chemistry on whole. If we try to study organic in the easiest manner, we can picturize or we can visualize all the molecules or all the families in the organic chemistry into this particular table. We can divide all the families, function groups you will basically meet in organic chemistry in this table. Okay. So basically there are five oxidation levels: 0, first, second, third, and fourth. Okay. And what is the meaning of oxidation level over here? The oxidation level over here is determined by number of bonds between a carbon and heteroatom. Means, if in a family you look at one carbon and see the number of bonds of that carbon with any heteroatom. Heteroatom is atom other than carbon and hydrogen. For example, in alkanes, we have got only the bonds between carbon and hydrogen. So there is no bond between carbon and heteroatom. I have already told heteroatom is atom other than carbon and hydrogen. So alkane is at 0 oxidation level. Now we will go to first oxidation level. So you can see here I have written alcohol family, ethers, haloalkanes, amines. Okay, what you can see common in these families are: there is a carbon which is attached to a heteroatom by a single bond. There is one bond between a particular carbon and a heteroatom. Similarly, you can see in this ether, if I write dimethyl ether, we have to take a carbon only, one carbon only. We cannot see this carbon and this carbon together. If we take only this carbon has got one bond with oxygen only. So this will be at oxidation level of alcohols only. Same at level of alcohols. Similarly in haloalkanes, here the carbon here has got only one bond with this halogen. So it will be at the same level of alcohols. Likewise the amines. You can see here this carbon is having only one bond with this nitrogen. Okay. So this is alcohol oxidation level. This can be called first oxidation level. Why? Because there is one bond between carbon and oxygen and heteroatom. Sorry. Then we move on to aldehydes, ketones, and acetals or hydrates or imines. What we can see here is there is a carbon which is attached to heteroatom by 2 bonds. This carbon is having 2 bonds with this oxygen. Likewise here in ketones also. In hydrates, there is a carbon which is having 2 bonds with one of this OH and the other one with this OH. So there are 2 bonds of a carbon with heteroatom oxygen. Likewise acetals, what you can see here is this carbon is having one bond with this oxygen and one bond with this oxygen. So it is also at the level of aldehydes oxidation level. Imines, you can see imines, this carbon is having 2 bonds with this nitrogen. Okay, so this is your second oxidation level or aldehyde oxidation level. Then we move on to carboxylic acid and its derivatives. What you can see over here, that there is a carbon which is having 3 bonds with heteroatom, 1, 2 and 3. In acid halides, which are acid derivatives, there is 1, 2 and 3 bonds. So there is a carbon which is having 3 bonds with heteroatoms. So the oxidation level of acid halides is same as that of carboxylic acids. Likewise, esters, this bond, and this bond. This carbon is having how many bonds with heteroatoms? 3. So the level of oxidation is same as that of carboxylic acids. Likewise, in anhydrides, carboxylic acid anhydride, this carbon is having 2 bonds with this oxygen and 1 bond with this oxygen. So the 3 bonds. Okay. Now we move on to cyanides or nitriles. What you can see, this carbon is having 3 bonds with this nitrogen. So this is at the same oxidation level as that of carboxylic acid. Amides. Okay. What you can see over here, that there is a carbon which is again having 3 bonds, 2 with the oxygen and 1 with the nitrogen. Okay. It is not necessary that all the bonds should be with the same heteroatom. Okay. If there are 3 bonds, it is third oxidation level, or popularly called as carboxylic acid oxidation level. Again, now we come at the carbon dioxide oxidation level. Here you can see the carbon is having, this carbon is having 2 bonds with this oxygen, 2 bonds with this oxygen. So there are total 4 bonds between the carbon and heteroatoms. So this is 4th oxidation level. Likewise, carbon tetrachloride will be at this level. CF4, CF3Cl, which are freons, I have mentioned over here. So, what is fun of dividing these families into these oxidation levels? First of all, we come to know one thing, whether we are going to do oxidation reaction or reduction reaction, or there is any involvement of any kind of oxidizing agent or reducing agent to carry out a conversion of one family into other. Okay. For example, if I have to move from 0 to higher oxidation levels, to alkane to carbon dioxide, for example, I have to carry out oxidation. From lower to higher oxidation level, if I have to move, I have to carry out oxidation reactions. Okay. If I have to move from a higher oxidation level to lower oxidation level, then I have to carry out reduction. Is it okay? So, if I am particularly moving at one oxidation level only, there is nothing like oxidizing agent or reducing agents, or no oxidizing agent or reducing agent should come into my mind. Okay. I will explain to you how we can study the conversions of one family into another at particular oxidation level using simple reagents. Okay. If we are considering only one oxidation level, if we are considering conversion of alkyl halides to alcohols, for example, or alcohols to alkyl halides, alcohols to ether, what we are going to do? Okay. What should come into our mind? That is what I am going to do in this particular lecture. Or what kind of reactions aldehydes and ketones show, I am going to teach you in this particular lecture. Okay. Then there are alkenes and alkynes, which are commonly encountered. I have not written aromatics over here. They will be part of these. I can take benzyl alcohol or something like that. That will be discussed in the coming lectures. Alkanes, alkenes and alkynes. You have studied that in order to convert alkene, for example, vanaspati, if I want to convert edible oil into vanaspati ghee, I have to carry out hydrogenation reaction. I have to add hydrogen. So addition of hydrogen is reduction reaction. So alkanes and alkenes cannot be at the same level. Likewise, alkynes cannot be at the same level of alkenes. So I have categorized them into different categories just to complete my table. The alkane is at the 0, then the alkene at the first, and alkyne at the second. Okay. Now we will study. I will show you the magic, or how we can study, or we should study organic easily and more effectively. For example, I am going to take this level, the alcohol oxidation level, and I am going to discuss some reactions. For example, if I want to convert, I am going to take this level now in this particular lecture. In the second lecture, in the second video, I will cover this oxidation level, conversion of this into this or this into this. Okay. In the third lecture, I will cover this easily. Okay. And then we will move on to oxidizing agents or reducing agents, which are typical reactions, or some typical reactions, or some extraordinary reactions shown by a particular family. Only that will be discussed in later on in the coming lectures. But here how we shall approach organic chemistry, I'm going to tell you. Okay, and that is going to make your life a lot easier while studying organic chemistry. Okay, today we will discuss some of the conversions at this level only. Okay, so let's go. Okay, for example, I am going to use what we have got, particular conversions. We can see that one thing that is called ethene or to ethanol. Okay, how are we going to approach this problem? You can see clearly these are at the same oxidation level, so no harsh reagents should come into my mind. Whenever I do conversion, I must know common naming or IUPAC naming of the compounds, because once I can convert a structure to a name or name to a structure, my life is a lot easier while studying organic chemistry. For example, this is ethene and I want to convert it to ethanol. I have written over here. Okay, now what you can see, now figure out what is the difference between the two, the starting and the product. I'm not going into the details of the reaction right now. Okay, so for example, the starting has got 2 carbons and 4 hydrogens. Molecular formula, here the molecular formula becomes C2H6NO. What is the difference between the two? The difference between the two is, you can clearly see there is difference of H2O. So I have to add water just to convert ethene to ethanol. Okay, clear? Now I must go into detailed studies of how to convert alkene into alcohols. We will study a detailed discussion, or we will study them in details. The alkenes, first of all, to do that, I will not only give you a lecture upon alkene to alcohols, I will give you a lecture upon alkenes to haloalkanes also in this video or the next coming video. Then I will show you the conversion of what we call them as alcohols to haloalkanes. Okay, then alcohols to ethers can also be covered, to ethers. And then the fifth one is alcohols to amines or alkyl halides to amines. Whatever we want to study, we will study. Okay, I will give you detailed discussion of this thing now. First of all, let's see what kind of reactions we will accept or expect in the given family. Okay, let me show you before we study this. The reactions which you can commonly study, which you will study in organic chemistry, basically they are reactions commonly encountered in organic chemistry are what? First of all, the reaction are substitution reactions. Substitution reactions. Then there are, we will come across what? And then addition reactions. I will write over here now, addition reactions. Then there are elimination reactions. Okay, substitution, addition, elimination. Then you will encounter pericyclic reactions. And then there are oxidation and reduction reactions. Reduction reactions. So substitution reactions means, substitute means what? It means to replace an atom or a group with another atom or a group. Okay, we have to replace one atom with another atom or one group with the other group. That is called substitution reaction. Okay, so these are basically, they are of three types. Okay. Substitution reactions are of three types. First is free radical substitution reactions. Free radical. Then there is nucleophilic substitution. And then there is electrophilic substitution. Okay. So these are basically various kinds of substitution reactions. Three kinds of reactions are there: free radical, nucleophilic, and electrophilic substitution reactions. Okay, the free radical reactions, substitution, particularly free radical substitution, they are demonstrated by alkanes. They are given by alkanes. Why? Means a free radical will be generated. So I will go into details later on. The free radical reactions are shown by alkanes, and the condition for a free radical reaction is sunlight, HNu, or UV, light, or peroxide, anything like that. These are the conditions to carry out free radical reactions. So any kind of reaction you will see happening on alkane, they will generally happen in these conditions: heat, light, peroxide. Heat is also there. Heat, light, peroxides. Okay, anything can be written. These are the conditions. These are mandatory. Something from this should be written on the arrow part. Okay, then there is nucleophilic substitution. Nucleophilic substitution means I can see I have to write alkanes, ethane over here, and then I can write nucleophilic substitution reactions. To show them, I must write an example of alkyl halides. Okay, then I can write alcohols over here also. Okay, I'm not writing amines. Okay, I'm writing alcohols. Okay. You can see on the basis of electronegativity difference, which is known to you very well, there are single bonds in this family and this family is also. The entire family, these three families which I have shown to you, have got only single bonds. Okay. Then, so one thing I can do to memorize is that substitution reactions happens in families having single bonds. Or happens at single bonds. Because, okay, what kind of substitution will happen? It is shown by, or can be known by looking at the structure of the families. You can see here there is halogen, and the electronegativity difference, due to the electronegativity difference between the carbon and the halogen is being more electronegative, carries a negative charge, and there is a partial positive charge at this carbon. Okay, so then what happens? Similarly over here, Oxygen being more negative, it carries negative charge, and there is positive charge over here. Okay, so it means the carbon is positive and it is like a nucleus. So single bonds are there, there will be substitution. Whenever I can see a positive charge on a carbon, as in present situation, I can write the word nucleophilic. Nucleus means a substitution reaction is going to happen in which manner? By using a nucleophile or the nucleophilic substitution reactions. Means alkyl halides and alcohols show nucleophilic substitution reaction because a nucleus is created at this carbon where the group is attached. Okay, this group is going to be replaced. This one here, in this one, this is going to be replaced. Okay, or substituted. In alkanes, hydrogen is going to be replaced by some other group. So, but in case of alkanes, we know that what? We know what? An sp3 carbon and hydrogen attached to it means sp3 hydrogen. sp3 carbon and hydrogen attached to it have nearly same electronegativity. Nearly same electronegativity. So therefore, I cannot put a negative charge on this hydrogen and a positive charge on this carbon. So they will pull the electrons of this bond with equal ease. Okay. So what can happen? If the bond breaks, you know the bond is made of two electrons. When the bond will break, one electron will be carried by this group and one electron will be carried by the hydrogen. So we will get free radicals. Homolytic cleavage will take place. So alkanes show free radical substitution reactions. Why? Because the carbon, which is sp3, and the hydrogen attached to it have got nearly same electronegativities. While in the case of alkyl halides or alcohols, you can clearly see that we can put negative charge on what? The halogen or the hydroxyl group, and there can be a positive charge on the carbon at which the hydroxyl group or the halogen is attached. So a nucleus is created. There are single bonds only. I can expect a substitution reaction only. But by which mechanism? By nucleophilic substitution reaction mechanism. And there is then the third kind of reactions which will happen. And those reactions are electrophilic substitution reactions. Electrophilic means you can see these happen aromatics. These are shown by aromatics only. Electrophilic substitution reactions happen only at aromatics. I will basically start with benzene reactions. Benzene is perfect example of aromatic compound. So you can see here there are pi bonds in the benzene, and these pi bonds are actually delocalized. So the another resonating structure which can be written for the benzene is this one. So there is alternate double and single bond, and you know the pi bonds are quite weak bonds. These bonds are quite weak bonds, and these bonds can be easily broken, or these can be written as there is electrons. So the benzene ring is quite rich in electrons, so it is actually supposedly carrying a negative charge. So what will happen if I will try to carry out a reaction at benzene? If it is having a negative charge, any reagent you add into the compound or the given reaction, it will always have two parts. For example, if I want to do bromination at benzene, it will have positive part and a negative part. This induced dipole kind of thing, dispersion forces. You know this thing in case of matter. This bromine can have a positive charge and this bromine can have a negative charge. And in presence of Lewis acid, simply FeCl3, something like this, what will happen? Either Br negative will approach first or Br positive will approach first, because the ring is negatively charged, because it is rich in electrons. So it will repel the negatively charged bromide. It will attract what? This brominium ion towards itself. So electrophilic substitution reactions means that positive part of the reagent will attack or will come first in the reaction and later on followed by negative part if required. Because we are going to substitute this in do substitution only, the negative part will not come. So therefore, what will happen? A bromine will replace an H, and H positive will be removed from here. H positive moves out. I have written it in a very poor manner just to make it exemplary that H positive is coming out. H positive will combine with Br negative and HBr will be generated. Okay, so why the bonds, you know that pi bond is weak bond, it is not broken. The single bond between the carbon and hydrogen is broken. There is substitution. Hydrogen is replaced by bromine. It is not adding, it is a substitution reaction which is happening at single bond. What I have stated earlier, that substitution reactions happen at single bond only. So why the pi bond is not broken over here? Because this is aromatic. If I will try to break this pi bond, I will try to do addition reactions on this benzene. Those will be very difficult because when I will try to add a reagent, its aromaticity will be lost. So the aromatics show which reactions? Electrophilic, substitution reactions. These are three kinds of reaction which you will expect. Okay, wherever electrophilic word is written means that molecule should be rich in electrons, and from the outside a positive part of the reagent will approach first. And in nucleophilic substitution, there must be a electron deficient center created in the molecule, like in the alkyl halides or alcohols. You can see there are positive charge in this carbon and this carbon. So the negative part of the reagent will approach first. Okay, so first and only because there is substitution, the positive part will never come in the substitution reactions. If there is nucleophilic, negative part will replace negative part. In the electrophilic substitution, positive part will be replaced by the positive part. And free radical reactions, these are simple kind of reactions. Okay, we'll study them details. These are the reactions and what kind of families show which kind of reactions. You must ask me, sir, that why I have not written amines over here, because amine is a very poor leaving group. Because more basic a group which moves out is, the less poor is the leaving group. If you can see, if I compare hydroxide and amide, which is a better base. Base is a substance which gives electrons, and I know by electronegativity that nitrogen is less electronegative than the oxygen. Therefore, it will donate electrons easily, so it is a stronger base. Amide is stronger base than hydroxide. So therefore, what should I know that? I have stated earlier that poor is the leaving group as the base strength of the leaving group increases. Leaving group, as it becomes more basic, its tendency to leave decreases. Means amines will not leave easily if you try to do the substitution reactions at amines, nucleophilic substitution reactions. So alcohols and alkyl halides show which kind of reactions? Nucleophilic substitution reactions. I will demonstrate them further. Now we shall move to next kind of reactions. Those are again addition reactions. Addition reactions, some kind. These are also three kinds. One are free radical additions, reactions. Okay. Then there is what we call nucleophilic addition reactions. And then there are electrophilic addition reactions. Free radical addition reactions, there are not many examples of the free radical addition reactions. So there is one reaction that is addition of HBr to alkenes in presence of peroxides. Alkenes in presence of peroxides. And also the addition of CC, for example, CCl3Br added in presence of peroxides. These are two kinds of reactions which are examples of free radical addition. This will happen in alkenes only. Okay, nucleophilic addition reactions. nucleophilic addition reactions. I will try to explain this by comparing what I can write here aldehydes. I can write here, I am writing it in a very poor fashion. I must write it like this, keeping the respect of the bond angles of sp2 carbon. And then there is what? Alkenes, and there are alkynes. Okay. Addition reactions generally happen at multiple bonds. Where there are multiple bonds, there you will expect addition to occur. Addition reactions. Okay. Free radical addition reaction, alkenes, I have demonstrated. These are two examples. Now there are two kinds of families you will encounter, or you can write cyanide imines over here. I can write what? Oh, I must shift something down the lane over here. Okay, and I shall write. Then there is, write in smaller way, aldehydes and ketones. And then there are what? Cyanides. Then there are imines. Okay. So these are, and there are some kind of families in the this alkenes and alkynes. What we can check over here? What we can check over here? Yes, come on. A multiple bond is here also, and multiple bonds are here also. In these alkenes and alkynes, and here in aldehyde, ketones, cyanides, and imines. What is the difference between the two? What kind of addition reaction will they show? I have explained you earlier also. What? There is a negative charge in this oxygen and positive charge in this carbon. Similarly, here, 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 here. What you can see, I have already told, if a carbon is generated with a positive charge, or carbon is assumed to carry a positive charge, you can assume a positive charge on a carbon, then you can write the word nucleophile on before the kind of reaction you expect in the family, because the family is having multiple bonds and single bonds, and you know pi bond is weaker than the sigma bond, so there will be chances of reaction at the pi bond easily. So here, this will show, these families show what kind of reactions? Nucleophilic addition reactions. These show these kind of reactions. Nucleophilic addition reactions means if I add a reagent, which part of the reagent will come first? If I add water, there is positive on the H and negative on the hydroxide ion, which part of the reagent will approach first? Nucleophilic, because there is a positive charge, so this is it. H2 negative will come first and H positive will come in the later part. Addition is going to occur, the whole reagent will add somehow. In electrophilic addition reaction, see, this carbon and this carbon will pull the electrons of pi bond with same extent. So and pi bond is weak bond, so there is you can assume a negative charge on this molecule, because as we assumed in aromatics. Okay, so here there are two negative charges like these pi bonds. Okay. One negative charge consists of two electrons. Keep that in your mind. Free radical does not have any kind of charge because it is having only one electron. Okay. A negative charge signifies a lone pair. Means there is two electrons. Okay. Now, alkenes show which kind of, because there is pi bond, a negative charge I can visualize on this molecule. So these show what? If I add water here again, which part of the because the molecule is carrying negative charge, the positive part will come first and negative part will come later on. Okay, is it okay? So alkenes and alkynes show which kind of reactions? Electrophilic addition reactions. Then there are eliminations. Okay, elimination are just the reverse of the addition reactions. Okay, then let's move ahead. Pericyclic and oxidation we will study later on. Let's move ahead. I think let's move. Okay, now continuing our topic, that which families show which kind of reactions. We have just discussed that alkenes and alkynes show electrophilic addition reactions. Just discussed. Electrophile is species which is electron deficient, so it is generally represented by E with a positive charge. Positive charge signifies that the species is electron deficient. It is not necessary the molecule in the whole is carrying positive charge. It is electron deficient. Electrophile is represented by the symbol E positive. Okay, over here. Then alkenes and alkynes both show electrophilic addition reactions. Now the next question which should come to our mind is, if I try to add a reagent into alkene or alkyne, out of the two, which reaction will occur fastly, alkynes or alkenes? Okay, let's try the structure first. Okay, sorry, this is your alkyne is over here, so I will write alkyne over here and an alkene over here. Now see what if I add a reagent. For example, I am adding water. Electrophile part of water is H positive. Okay, so H positive is going to come. There's one negative charge. If I donate a pi bond by one negative charge, and there are two negative charge over here, that means this molecule is more electron rich than this. Alkynes are more electron rich than alkenes. So what should happen? The reaction should occur fastly over alkynes compared to alkenes, because it's more electron rich. You can see over there. But alkenes are more reactive than alkynes. Why? First of all, these are some of the reasons which are responsible for the observed behavior. The first is hybridization. Hybridization, you know very well that in alkenes the carbon is sp2 hybridized, and in alkynes the carbon is sp hybridized. The more is the s character in the hybridization or hybridized orbitals, the more is the electronegativity of an atom. If you compare carbon over here and here, the percentage of s character in sp hybridized orbital is around 50%. 50 is s character, 50 is p character, and here there is 25 and 75. Oh sorry, 64 and 36, something like that. Okay, here the s character is 36 and p character is 64. Okay, here the percentage of s character is increased. Now the s orbital lies closer to the nucleus. You have already seen, according to quantum, as the first come the s orbital, then the p, then the d, then the f. The s orbital lies closer to the nucleus, means the electrons here in the alkynes are closer to the nucleus. They cannot be donated to the incoming electrophile. The electrophile is electron deficient. It wants electron. It is just like that. If there are two persons, and one is having $100 and the other one is having $500, and a person from outside desires to have $100, who will give him the $100 more easily? As expected is that the person with the $500 should give the $100 to the one desiring or demanding the $100 or requiring the $100, but it never happens. It will only depend upon whether the person is extravagant or miser. If the person is miser, even after having $500, he will straight away deny that I have no money. While the person who is extravagant, who is just spends like anything, he will donate the amount easily or give the amount easily. Similarly over here, because alkenes is having sp2 hybridized carbon, which is less electronegative, it will give the electrons easily to the incoming electrophile. Okay, clear? This is the first reason. the hybridization of the carbons in alkenes and alkynes, because alkenes is sp2 hybridized and the carbon in the alkynes is sp hybridized. The more the s character in the hybridization, the more the electronegative the element will be, so it will not donate the electrons easily. If it will not donate the electrons easily, the reaction will not occur at a faster rate. The second reason is stability of carbocation or the bridge intermediate form. There are two kinds of intermediate form when the reaction happens. There is cation and the bridge intermediate. Whether the reaction happens on alkenes, on alkynes, if I add H positive over here or H positive over here, what will happen? I will get what? This pi bond will be shifted over this carbon, for example, and this pi bond is shifted over this carbon, and then the reaction happens on this carbon. Okay, what we will get? We will get CH2, CH3, because when the pi bond is shifted over here, both the electrons of the pi bond get shifted on this carbon, and this carbon will become electron deficient, so it will become a positive, it will carry a positive charge. Similarly over here, if I try to make this, I will get what? This and a positive charge over here. Here I got a alkyl cation, and here I have got a vinyl cation. Of the two, you better know that the alkyl cations are quite stable while the vinyl cations are quite less stable, so they will not be formed easily. This will be formed easily, which is formed when the electrophiles adds on alkene. Because this is formed easily, the reaction will occur at a faster pace. If, on the contrary, if the reaction involves the formation of bridge intermediates, like the formation of if I try to add bromine, there is formation of bromonium ion, okay, in alkenes, and in alkynes, if I try to do the same kind of reaction, what will happen? This bridge intermediate is having what? It is having a double bond. So double bond means the angle will be around 120, should be 120, but due to strain, the angle is 60 degrees. I have to shift, the angle has to be shifted from 120 to 60. This ring is very unstable, but here the carbon is sp3 hybridized, okay, assumingly. So this here the ring is having lesser strain than this, because this bridge intermediate is more strained than this will not be formed easily. This will be formed easily. So the reactions generally of alkenes and alkynes will either involve formation of cations or the bridge intermediate. In both the cases, you can see if the cation is formed in the alkenes, it is more stable than the vinyl cation. If you try to form a bridge intermediate, the bridge intermediate is more stable in the case of alkenes than the case of alkynes. So the reaction will happen at a faster pace in the alkynes than compared to alkynes. The alkenes will show faster reactions. And now the last reason we can account is the pi electron cloud in alkynes is cylindrical. Because it is cylindrical, you know that. So it is more delocalized and it's not easily available. So if it is not easily available, it will not be donated easily to the incoming electrophile. So the reaction will happen at a lower pace. These are some of the reasons which are responsible for the observed behavior. And one more question which is often asked: if in the reactions of alkenes or alkynes, electrophile approaches from the outside, then your given compound is nucleophilic. This is nucleophilic. It attacks at positive center. Nucleophilic thing is the one you label a compound as nucleophilic, which attacks as positive charge. So you can see it is attacking over here. So the alkenes and alkynes are nucleophilic. They attack at the positive charge. And whenever you write the mechanism, make one thing sure: never draw an arrow from positive to negative, because positive signifies a nucleophile. This is a commonly encountered mistake or made mistake by the students. You should write a mechanism showing the movement of arrows correctly, that a negative charge should attack a positive charge. Electron should be moving like this. The arrow should be going like this. It is correct, because electrons are outside, nucleus is inside, and in reaction electrons participate, not the nucleus, except the nuclear reactions. You know better. Okay, that's it. Similar on this. So generally what you will see that in the cases of alkynes, the reaction happens in the presence of mercury as catalyst, or something other catalyst, some other catalyst in the metal catalyst, while alkenes generally don't require such kind of catalyst. The reactions at alkenes are easier. Okay, I will show you the reactions in the coming lectures. Now, having discussed this, I will discuss the another kind of addition reactions. As we know that aldehydes and ketones also show nucleophilic addition reactions, but of the two which show faster nucleophilic addition reactions, we are going to cover that topic now. Just a minute, I will erase this first. Now, we continue our lecture. I'm going to discuss now the order of reactivity of aldehydes and ketones towards nucleophilic addition reactions. Nucleophile is something which is positive charge loving, so it should be electron rich. Phile means loving, and nucleus means nucleus loving. So here I can see there is a positive charge, a negative charge on this carbon, oxygen, and there is a positive charge over here, a negative charge here, positive charge here. So what I can expect, what should happen? If I add a reagent, for example HCN, water, something like that, alcohols, what I should expect? The negative part of the reagent must approach. So it should attack here. It should attack here, not on the oxygen. By negative, you can see there. The bonds get shifted over here, the bond gets shifted over here. Okay. Which reaction should occur fast? There are two reasons for the same: electronic factors and steric factors. Two reasons that you can see here. The more is the positive charge over here, the faster will be the reaction. If you see, there is one alkyl group and there are two alkyl groups over here. Okay. Alkyl groups, as you know, alkyl groups are electron donating. They are electron donating. They will donate the electron to this carbon. Now you can clearly see here there is only one group which can donate electrons. H is electron donating, but not to that extent as that of alkyl groups. So there is only one such group which can donate electrons easily, while in case of ketones there are two alkyl groups which can donate electrons easily to this positive charge carbon. Means these two groups will reduce the positive charge at this carbon more than this. But here the positive charge will be more because there is only one electron donating group present. Okay. So the reaction over here will be faster because there will be an increased positive charge here compared to there. So the reaction, the nucleophile will be attracted here fastly. Now comes the second reason, which is steric factor. The steric factors means whenever the reaction happens, the molecules should collide with proper energy and proper orientation. If there is just if they have the proper energy to cause the reaction, but the molecules orientations are not correct, they are not reaching towards each other at the position where the reaction should happen, the reaction will never happen, the reaction will not go. So here you can see there's one R group, alkyl group. The minimum alkyl group can be CH3, smallest, and here there are two groups, alkyl groups. No, because the CH3 is quite bulky. As the bulkiness of these groups increases, the nucleophile will have a lesser space to attack at this carbon. So due to lesser availability of space, it will not be able to attack this carbon easily, while here, because there is only one alkyl group, it will attack at this carbon more easily. So the reactions, aldehydes show a faster nucleophilic addition reactions than the ketones. Okay, it is presumably believed that it attacks the nucleophile because it's sp2 carbon. So this it should attack like this at 90 degrees. The attack never happens at 90 degrees. It is at somewhere around 107 degrees, something like that. Angle is there and nucleophile is attacking. Okay, that is Lewis angle. Okay, the attack is at somewhere around 107, 106 degrees, not at 90 degrees. Nucleophile never attacks at 90 degrees to the carbonyl carbon. The carbonyl carbon is a carbon oxygen double bond. Okay, I hope you got the lecture. As the bulkiness of these group increases, there is only one group. There are two groups over here. Nucleophile has lesser space to reach this carbon. If it is not able to reach this carbon, the reaction will definitely get slower because the reaction is going to happen at this carbon. So these are two reasons that aldehydes show a faster nucleophilic additions than ketones. And if you are comparing similar in aldehydes only, as you can see in aldehydes, this R group can be changed, and as the size of the R group increases, the rate of reaction will decrease. For example, if you are comparing formaldehyde and acetaldehyde for nucleophilic addition reactions, the reactions at formaldehyde will be faster than the acetaldehyde, and so that likewise the case. There are examples you can study. Okay, thank you. The lecture is over. Now in the coming lectures, I will discuss the reactions of alkenes and alkynes and the reactions of ketones and aldehydes. Okay, thank you.